Hi everybody, today we're going to start talking about free body diagrams and how we use them to determine net force. As we've been saying in class, we have to look at all the forces or the sum of the forces in order to exert it on an object to really determine whether or not the object is going to change its motion or accelerate. So our objectives for this lesson are to be able to draw and label a free body diagram and then perhaps be able to determine the net force exerted on an object using that free body diagram. So first of all, what is a free body diagram? It's simply a drawing that's used to show the size and direction of all the forces that are exerted on an object. So you can see I have a picture here that has a person riding a motorcycle, and there are several forces exerted on the object. When we want to draw the free body diagram, though, we want to be able to determine the net force. So we want to simplify the drawing as much as we possibly can. If you remember back to when we talked about motion diagrams all the way at the beginning of the year, remember we took out a lot of the complication of the object by representing it with a dot. And we're going to do the same thing here when we use a free body diagram. We're going to represent the object or the system, because we have two things actually moving here. We have the motorcycle and the person, but we're going to consider them all one thing as they move, and we're going to represent that by a box. Some people will also use dots. You can use a dot to represent it. I just find a box is a little bit more easy to visualize. So the first thing we do when we draw a free body diagram is we replace the object with a box. Then what we use is we use vector arrows to represent each force. And we draw them first of all to size, to scale. If you remember when we started talking about vectors, they have a size, they have a direction. And when we draw that vector arrow, it had to be scaled appropriately. So when we look at drawing our arrows that represent our force vectors, we draw them to scale. So if one force is bigger than another, we make that arrow bigger than the other. So you can see here that we have four forces being exerted on this object. We have a force due to gravity, which is the weight of the object, which is pulling down because, of course, gravity always pulls down and everything experiences a force due to gravity. So as a result, for your free body diagrams, you are always going to have a force due to gravity or a weight exerted on the object in the downward direction. The object's traveling along a road, we assume, and as a result, it's not changing its motion in that vertical direction. It's not plummeting towards the center of the earth. So there must be some force that is balancing out the force due to gravity or the weight of the object. And that's this normal force here. Remember we said a normal force was a support force provided by a surface perpendicular to the surface. And in this case, it balances out the force due to gravity that's exerted on the object. We also have two other forces that are exerted. We see this force that is an applied force. That is probably due to the engine of the motorcycle. It's pushing the motorcycle forward. And then last but not least, we have this frictional force. And remember, if you look at it, we could tell the motion of the object, which direction it was moving, because the friction force always opposes the direction of motion. So for example, even if we weren't looking at the person sitting on the motorcycle, we would know that this object is moving to the left because the frictional force is to the right. It's always opposite the direction of motion. And the frictional force in this case could be due to the tires moving over the surface of the road, the air resistance that the motorcycle and the person encounter, but we're just going to look at it as the sum of that frictional force. So if you look at these, the magnitude, we can tell that the normal force is equal in size to the gravitational force or the force due to gravity or the weight of the object. Here you can see that the applied force that the engine is providing is greater in size than the frictional force. So as a result, there's going to be a net force exerted on this object. They don't all balance out. All right, so when we draw our arrows representing our force vectors, we draw them in the direction that the force is actually acting. And this is one thing you have to watch. If the applied force for this motorcycle engine is pushing it to the left, and that's what you think about, that applied force is pushing the motorcycle and the person to the left, you do not draw the arrow going from the right into the box. meaning in that left direction. We always draw our directions for our force vectors radiating out from the box in the direction that they are going. So that's why this applied force, even if you might think it's sort of pushing it along, it almost looks like it's actually pulling it along because it's going towards the left, but we draw all our force vectors radiating out from that box that we use in our free body diagram. The last important part is to remember that every force arrow vector that you draw in your free body diagram must have a source. If you cannot say what type of force it is, meaning what is causing that force, is it gravity, is it the support of the ground to provide the normal force, if it's a frictional force because of the motion of the object over a surface, the force does not belong there. You should be able to say the contribution or the cause of every force that is labeled on your free body diagram. And you get that information from your question or your problem. This is not something where you look at the free body diagram and you're using it to tell you the forces that you have, but instead you're using it to organize and simplify the forces that you have so you can find out if there's a total net force. Let's look at some quick examples. Here we have a penny. It's dropped from the Empire State Building and it falls freely to the ground, and it tells us to ignore air resistance. So I have my box that represents my penny. If you remember from free fall, when we talk about ignoring air resistance, the object is only moving under the influence of gravity. So the only force that is affecting this penny's motion is gravity. And gravity always points down. So this would have a force of gravity. I can say what it's due to, and it would be in the downward direction. That's it. There are no other forces exerted on the object, so I would know that there's a net force because the force of gravity is not balanced out by any other force. All right, now what happens if we drop that same penny from the Empire State Building? It still falls freely, but we do not ignore air resistance. Well, we're still going to have that force due to gravity, and it's still going to be pointing down. But in this case, we're going to have some type of force of friction that opposes motion. Because remember, that's what air resistance really is. We talked about that. Air resistance is a friction force, although you could actually call it an air resistance if you wanted to. All right, but this would tell us now that we have two forces being exerted on an object, and we don't know whether or not they're balanced just yet. We don't know anything about their relative sizes, but we're going to learn a little something next in the next slide that would tell us. This would be all the forces that are exerted on the object. If we knew the sizes, we could determine the net force. All right, let's go to another one. Here's the same penny being dropped by the Empire State Building. We're still not ignoring air resistance, but it tells us that it's traveling to the ground at terminal velocity. Now, you may have heard that term before. Terminal velocity is the speed that falling objects reach when the air resistance balances out the force due to gravity and you no longer accelerate. So when you're falling out of an airplane, or when this penny is dropping from the Empire State Building, there's eventually going to get to a point where the air resistance is so large that it balances out the force due to gravity and there's no acceleration because there's no net force. So in this case, we would still have a force due to gravity, or the weight of the penny, and we would know that the air resistance, or that frictional force, was exactly equal and opposite because it balanced out our force due to gravity, or our weight. Terminal velocity means you're moving at a constant velocity, which means you have no acceleration. And if you have no acceleration, your forces are balanced. How about a textbook sitting on a table? So now again, always that textbook is going to have a weight. It's going to experience some force due to the gravity of the earth. And because we know that the textbook is just sitting still, we know that there's no change in its motion. We know that all the forces must be balanced. So there's a normal support force that is equal and opposite, meaning equal in size and opposite direction, that is providing that support. The table essentially is supporting the book and providing a force that balances the force due to gravity or the weight of the object. That's it. That one's done. All right, now what about a student starts to push that textbook across the table to the right with a constant velocity? Well, even though our motion is in the x direction or the horizontal direction, doesn't mean our weight goes away. We still have our force due to gravity, our weight of our object. We still have our normal force balancing it out because the object is not moving or changing its motion in the vertical direction, so those two forces still have to exist. But here's something, the student's pushing. So we're going to say pushing it to the right. So here's where I said even though it looks like you would want to put the arrow into the box coming from the left and going towards the right, we're going to draw all our forces radiating out from the box. We want to look at this and we want to say, well, you know what? If this applied force is the only force in that horizontal direction, there's a net force in that horizontal direction, and that book should be accelerating as it goes across the table. Well, the fact that it's moving at a constant velocity tells us that the force in the x direction has to be balanced. There is no net force because we have no acceleration. That's because we also have, again, a frictional force as it moves over the surface of the tabletop. And it's opposite the direction of motion, so it would go to the left, and that frictional force balances out the applied force so that the object can travel at constant velocity. Okay, one more. Now the student pushes the textbook to the right, but now it's accelerating, which means it's changing its motion. It's getting faster and faster as it moves across the table. So once again, we still have our weight or our force due to gravity pulling down. We still have our equal and opposite normal or support force. All right, we're now going to still have an applied force, but whereas in the last problem, our force of friction balanced out our applied force, meaning it was the same size but in opposite direction, so that we had balanced forces and no acceleration. Here we have an acceleration. So that must tell us that our frictional force is less than our applied force. It still exists, but as you can see, I'm going to draw it, and I'm not going to draw it anywhere near as large as my applied force. And that's it. If I knew the numbers of these, I could then go and use those numbers to determine the net force that's being exerted on the object.